Hello everyone, and welcome to yet another review session for your final exam in calculus from MA3208. Today we're still inside the calculus of trigonometry category, and we're looking at graphs of inverse trig functions. So this is not necessarily a calculus topic as such, it's more of a pre-calculus topic, but since it's something that doesn't really get covered in your 3200 course, we tackle it here. So we're going to look really quickly at some notational issues first before I even jump into the introductory slide. Those of you who are familiar with the buttons on your calculator for inverse trig functions, inverse sine, inverse cosine, and inverse tan, you should remember that if you ever see it written this way, as arc sine of x, arc cosine of x, or arc tan of x, that's another, it's actually a better notation, but whether it's too long-winded or it doesn't fit on a calculator button, either way, these are better notations. But we're going to run with these for now because they're the ones that are used both in your textbook and probably on your exams, etc. So just keep in mind that they mean the same thing. Alrighty. So let's see the kind of topics we're going to discuss in detail here today. We're going to use the properties of inverses. So what does it mean to be an inverse function? We've got to remember a bit of that. We're going to use those to sketch the inverse trig relations. So that's what we're after, sketching the inverse trig relations. And then we're going to restrict those relations when we get their graphs to create functions out of them. So we're going to make functions out of those silly little relations. And then we're going to talk about defining the principal values of an inverse trig relation. So this thing, principal values, is really important. We're going to get into that. Okay? Let's get started. So first of all, we're going to try and get the inverse of sine x. And this slide looks like, whoa, that's a lot of stuff all at once. But just hold tight for a second. Try and follow me through this. So if we look at the original function we're going to start with, is just our old buddy f of x equals sine of x. All right, so you can see we're graphed here with our domain in radians. Range is going to be given in values from -1 to +1. Okay, so the domain and range for the original sine function are, x values can be anything we like unless it's a particular problem where they would have to be restricted, and the y values are bounded on an inclusive interval from -1 to +1. Now, what we have to remember is, way back when, probably in your 3200 course, you learned about something called inverse functions, because there is a section early on in that course about it. And if I were to think about what the graph of an inverse function looks like, you should probably remember that if I draw the line y equals x, so it's a diagonal line that goes through the origin like this at about a 45-degree angle. If I were to draw the line y equals x, now if my scale was 1-to-1, it would be exactly on that angle, but the scale is not 1-to-1 obviously, because what we're dealing with here is radians on one axis and something else on the other. So technically, if our scales are 1-to-1, it would go through like that. But in this case, it's going to actually go through more like an angle like this, because every block on the x-axis is actually pi over 2. But it'll look something a little more like that. So basically, what I want to do is, if I want to get the graph of the inverse of this function, is I want to take every point on the graph and I want to reflect it directly over that line. So for instance, this point down here would have to get flipped over. All the points have to get reflected directly over that line. And what it does is it kind of does this really funny flip-flop motion, and we end up with a graph that looks like this one, which is our second graph. So this is the inverse trig relation, y equals inverse sine of x. Now notice here, I said it's the inverse trig relation, and I didn't use function notation for my dependent variable. We'll talk about why that is in a second. But basically, that's how we arrive at what the graph of the inverse trig relation looks like. Now, I want you to remember in your 3200 course, when you were solving trig equations, when we solve trig equations, what we remember is that we'd have something like sine of x over here equals whatever. And when we solve it, we get a whole bunch of different possible answers, an infinite number of answers. That's kind of what's happening with this inverse trig relation. If I tell you that x on this graph over here is equal to 1/2, well, what's the value of y that would correspond to that? Well, I get 1, 2, 3, 4, 5 responses to that just on this one little section of the graph that I have drawn along. So if I let this graph continue on, there's an infinite number of y values that would correspond to that x value. That's not cool. In math, we don't like that. We say that that's not a function. And it's not a function because, if you remember all the way back to grade 10, you learned about something called a vertical line test. And if I draw a vertical line, or if I can draw a vertical line anywhere on my graph, and it touches the graph at more, or touches the curve at more than one place at a time, for one particular x value, it's not a function. And that creates all kinds of difficulty when we're working things out. We get multiple answers, and it's just messy. So what we do is we clean that up real quickly. We're going to restrict this graph, and it's not its domain we have to restrict here on this function, because its domain is bounded now anyway, because we flip-flopped our x's and y's. So we have to restrict the range of this graph so that we can have just enough of it so that we can get one value of y for every value of x. So the question then becomes, how should we restrict that? Well, let's get this thing out of our way for a second. How should we restrict this graph? Well, let's think about it. Let's start at 0, and we'll start drawing the graph right on here and see how far we can get before we run into trouble with not being a function. So if I start right at the origin here on this graph and I trace it this way, I'm doing fine here, but as soon as I get past this extreme value and I start to come back around, as soon as I start to come back in this way, all of a sudden I'm going to start to fail that vertical line test again. So what I do is when I get out to an x value of 1 or a y value of pi over 2, then I cut it off and I say I can't go any further that way or I'm going to fail. But that doesn't mean that's all I can have, because if I go in the other direction coming back this way, you see I can get back as far as -1 for x, which is negative pi over 2 for y. If I go any further than that, I'm going to be in trouble again. So that's about as much as I can take of this graph and keep it without actually having to violate a vertical line test. So if I keep just that much, we call that the inverse trig function. So that's actually f inverse, which is the inverse sine of x. Okay? So it's got a restricted domain because of the nature of sine and cosine. That's bounded between -1 and +1, just like the range was over here. But I can't take all the domain from the original sine and make it my range. I can only take so much of it. So we say that y has to be bounded between -pi over 2 and +pi over 2. And we call those values the principal values of the angle. So if we talk about principal angles or principal values of the angle for this particular function, that's what we're talking about. So for sine, our principal values were bounded between -pi over 2 and pi over 2. And when we use this notation, inverse sine, typically we're talking about the inverse trig function, which is this restricted version right here. Sometimes, and you'll see some textbooks and even some mathematicians, etc., when they talk about the relation, they'll write it this way, and when they talk about the function with the restricted domain, they'll either use a capital S on their inverse sine like that, or they might write their x with some funny notation or a capital theta. I've seen all different kinds of ways to do that to indicate that you're talking about a restricted one, but we'll be consistent. For our purposes, if I write this, I'm talking about only principal values, okay? So that's how we do this for sine. Let's take a look at cosine. Going to be a very similar situation. So for cosine, and perhaps I should have written the correct trig ratio here, cosine, cosine, and cosine. Pardon me, cut and paste gets out of control. All right, so those are all cosines. But when we look at this, it's going to be the same type of thing. The original graph of cosine has a domain from -infinity to infinity, and it's got a range from -1 up to +1 that's restricted. We know all about that. Then we've got to do the same kind of trick. I've got to take this graph, and I've got to reflect it over that magic line at y equals x. So a line that looks something like this, because remember we're not 1-to-1 on our scale here. So if I reflect it over that line, I get a picture that looks like this second graph that I have. So my picture ends up looking like this one. So that's all well and good, but for the same reasons we talked about with sine, that is not a function. So we're not allowed to keep all of it. So let's start at 0 and see how much of it we can keep. Well, we can't start at the origin here. We have to start where y equals 0 and x equals 1, I guess would be the most reasonable place. Now, if I'm going to go upward from there, that's fine, but I can't go upward and downward, because the second I go in two different directions from that point, if I go this way and decide to keep both of those pieces of my graph, we're going to be in trouble. So what we do is we forget about the negative stuff. We just go in the positive direction. We'll see how far we can get. So if I go in the positive direction, I wouldn't fail a vertical line test yet, keeping all of this stuff, until I would start to bend back around right there. So what we do for cosine is we keep a different restricted range so that we get an inverse trig function. What we do is we start at 0 for its range and go up to +pi. So the range is the same size, it's still pi units large, but it doesn't start at the same values. It goes from negative 2 pi, or pi over 2 to positive pi over 2 for sine, and 0 to pi for cosine. And notice, of course, that the domain of the inverse trig function is the same as the range of its original function. Okay, lots of fun there. You guessed it, there's one more. Uh-oh, tan. Well, you should recall that tan has a real cagey looking graph anyway, because remember, tan was sine over cosine. So wherever cosine was equal to 0, tangent gave us all of these really nutso vertical asymptotes happening all over the place. So we get all these vertical asymptotes happening here on the tan function. And that might scare you a little bit, but it actually makes it a lot easier to decide about what we're going to do when we restrict our domain. So let's picture our diagonal line going through the tan function like that. And then we're going to think about what would happen if I reflected everything I have over that line. And once again, if you can picture that in your mind's eye, we get a graph that looks like this. And so, again, we're going to fail the vertical line test ad nauseum here a zillion times. So what we do is we restrict. And the easiest way to restrict this one is just to keep this middle section of the tan graph between those two asymptotes. So our vertical asymptote sort of became horizontal, and we just keep that middle section. So we're going to hang on to everything between negative pi over 2 here and positive pi over 2, which was the same restrictions that we gave on our sine. So it's not like there's anything new here, except for one minor detail. With sine, we allowed ourselves to touch the endpoints of the range, the interval that we take for the range. With tangent, it's horizontal asymptotes at those places. And they were vertical asymptotes of the original, so we never actually touch those horizontal asymptotes. So you'll notice that I have to use the rounded brackets on the definition of my range here for the tangent function. Okay? So that's the inverse trig function for tan. And it's just that principal value range from negative pi over 2 to positive pi over 2. That's a lot of fun. Okay. There's not a whole lot of different types of exercises we can do with this stuff. But this is sort of the background information we need to go forward with our next topic. But something we can do is we can look at how do I determine the domain and range of an inverse trig function like sine or cosine. So let's try that. The ranges are real easy. You got to remember that for both sine and cosine, the range of the inverse is going to be what? Well, that's the part that we restricted. That's always going to be from negative pi over 2 to positive pi over 2 for sine, and 0 to pi for cosine. So for this particular one, we're dealing with a cosine business. So the range of this is going to be, y values are going to be going from 0 to pi, and we're allowed to include both endpoints for this. But the domain is a bit trickier. Remember now, our domain is restricted to be between negative 1 and positive 1 if our variable inside here is simply x or theta or whatever we want to call it. In this case, I've got this x squared minus 4. So how do we deal with that? Well, we're going to say that our domain here is still going to be restricted between negative 1 is going to be less than or equal to, and we're going to have positive 1 that we are less than or equal to for whatever our argument is, and our argument is now x squared minus 4. Okay, so with that, what I'm going to do is I'm going to add the 4 to all three sides of our three-sided inequality here, and get 3 is less than or equal to x squared, which is less than or equal to 5, and then I'm just going to take a square root. So I have square root 3 is less than or equal to x, which is less than or equal to the square root of 5. So we have a different type of boundary on the domain of this particular function. So that's a little bit different than it was when we were dealing with the other version of this. Okay? Let's try another one of these examples. Let's look at this one. It says f of x equals the inverse sine of the square root of x minus 4. So same idea. Let's get the domain and range here. Okay. Oh, and whoopsie, I just realized I forgot something on the previous slide. Back here, remember, if I take the square root, I can get a plus or minus answer. So we also have a possibility that we could be between negative root 5, and that's a negative, so I'm going to flip those signs around. And that would be less than or equal to x, which would be less than or equal to negative root 3. So we have this sort of disjointed domain here. All right, let's try another one. So for this one, it says determine the domain and range of this one. This is not going to be so bad. So again, the range, since we're talking about a principal value of an inverse sine function, the range is going to be bounded to be between negative pi over 2, and that's going to be less than or equal to y, which will be less than or equal to pi over 2. You can write these things in more proper notation, but for now we're just figuring it all out. And then if we look at the domain of this, so the domain of this particular function, we've got to be bounded between negative 1, square root of x minus 4, and less than or equal to 1. And so to solve for x here, what I'm going to do is I'm going to have to square both sides. So if I square both sides of this, I get 1 is less than or equal to x minus 4, which is less than or equal to 1. This seems kind of funny to me. Let's see what's happening here. So if I do that, I'm going to get, well, I'm going to add 4 to everything. So I have 5 is less than or equal to x, which is going to be less than or equal to 5. That's a bit fishy, isn't it? Let's see. If that's the case, does that mean that x could only be equal to 5? There's definitely something amiss here. So let's think about this for a second. It kind of makes you wonder why we got such a funny answer there, but let me try to explain this to you now. I want you to notice that this says a square root, and there's nothing in front of it, so it's a principal or a positive square root only. There's not really any need for me to say that it has to be bigger than or equal to negative 1, because we know it's always going to be greater than or equal to 0, isn't it? So whatever's in here is going to be greater than or equal to 0. So that means in order for this to work, I not only have to worry about the restriction on my sine function, I have to worry also about the restrictions on the square root function. So let's try this again. Let's be a little more specific. We're going to say that for any of this stuff to work out, what's inside here has to be restricted to be between 0. So we can't be any bigger than 0, or any less than 0, sorry, because the square root is never going to get there. So that's x minus 4, and that's got to be less than or equal to 1. So now I have 0 is less than or equal to x minus 4, which also is less than or equal to 1. Now if I add 4 to stuff, I can see that that gives me possible values for x that are going to stretch from 4 to 5. And yes, this is in fact the domain of this particular function. So if we're talking about that one, we're stuck between 4 and 5. All right, that's a lot of gunk going on there. And I don't want you to sweat too much, panic too much about this stuff. It's kind of important for us to see that when we're talking about these inverse trig functions, we have some fancy things happening. But as in terms of this example, I thought it was good exposure for you. But don't panic too much about it. So here's what I want you to do. Try the your turn question. In this one, it works out a lot smoother because we don't have any squares or square roots or anything crazy. So take a look at that, and if you want to try to work it out, that's a good idea. And then we'll take a look at the solution for it. So there's the solution, and it works out to be a lot nicer than what we had before. We're dealing with a sine function, so of course that's going to be our restricted range, and our restricted domain looks a lot nicer than what we had before. All right, so let's highlight some of the key ideas about inverses of trig functions. Okay, so let's try this now. It says the graphs of the inverse trig relations are the reflections of the primary functions over the line y equals x. True, just for the relations. So we restrict the range of the relations to allow them to become the inverse trig functions. And so when we do that, the restricted ranges of the inverse trig functions define what we call the principal values of these functions. So the y values, for sine, we're always between negative pi over 2 and positive pi over 2. For cosine, we're stuck between 0 and pi. And for tan, we're between negative pi over 2 and positive pi over 2. But oopsie doopsie, look what's not right here. This should be strictly, because tangent never actually touches those values, does it? So be careful with that one. Alrighty? Thanks very much. I hope that's at least a little bit helpful for you, but it's more or less just a background session so that we're ready for the next stuff that's coming down the pipe at you. Alright, see you next time.